video, we'll learn about some of the most used activation functions. And you guys already know like how ANN will be working. So this is some simple ANN structure. So the first layer, we call it as input layer, and followed by we'll be having hidden layers. So this we can call it as hidden layer 1, and then hidden layer 2. So on, we can have some n number of hidden layers. That is up to us what is the number of hidden layers. And finally, we'll be having some output layer, and through this we'll be getting the predicted output. And we know what are all the changes that we need to make according to the problem that we have. Let's say the problem that we are trying to solve is some regression problem. Then what is the activation function that we'll be using? If you have seen my previous videos, you will get to know this. So if it is a regression problem, the activation function that we use is linear activation function. And within classification, we have two types of classifications. Basically, one is binary classification, and remaining generally we can categorize them into multi-class classification problems. So if we are trying to solve binary classification problem, then simply we can use the activation function that is sigmoid. And if it is multi-class classification problems, then we can use softmax. This we have discussed in the previous videos itself. Let's try to understand about these activation functions in detail, and along with them we'll try to look into some other activation functions as well. So the first function that we'll look into is the linear activation function. And you guys already know what is linear activation function. It is really simple. For this linear activation function, whatever input that we are giving, like input can be anything which can be in between minus infinite to plus infinite, and similarly output will be the same. Whatever input that we give, the output will remain the same. So the output range over here is also from minus infinite to plus infinite. Okay. And if you see linear curve visually, that is on x-axis we'll be having x, and on y-axis also we'll be having the same x, because as the linear function is outputting the same, right? So that's why on y-axis also we'll be having the same x. And for input 1 we'll be getting the output 1, so that will be over here. And for input 2 we'll be getting output also to be 2, as both input and output are the same. So if we combine these all points, it will be a straight line that is passing through origin like this and connecting these 2 points. Okay, so this is the kind of line that we'll be getting if you are trying to draw curve of linear activation function. Okay, and while doing backpropagation, in the last video we have already discussed how backpropagation is being done. While doing that, we might need to calculate derivatives. So basically, if we calculate derivative for this particular linear function with respect to x, then it will be 1. Okay, so this is about linear activation function. And then we have sigmoid activation function, which is used for binary classification problems in the output layer. And sigmoid can be represented using this symbol, and the formula for this is 1 by 1 plus e power minus x. Here we can pass input to be anything, that is from minus infinite to plus infinite. You can pass any number, but the output that we'll be getting will be in the range of 0 to 1. Okay, so this will always be in the range of 0 to 1, whatever the input that we pass. And if we see this visually, that means on y-axis we are trying to plot about sigmoid of x, whereas on x-axis we'll be having the x. And we know that input can be anywhere from minus infinite to plus infinite, but the output is between 0 and 1 only, and the graph of sigmoid will look something like this. Okay, where this is 0 and this is 1. Okay, it will not cross 1 and it will not go below 0. So this is the graph of sigmoid function, and this we have seen in logistic regression as well. And as I said, while doing backpropagation, we might need to calculate derivative, and this is also differentiable, and its differentiation will come up to this sigmoid of x times 1 minus sigmoid of x. We calculate derivative of sigmoid x, we will be getting this one. This is about sigmoid activation function. And then we'll be having softmax as our activation function. The third activation function is softmax. Basically, you can think of it as some extension to this sigmoid. Basically, the sigmoid will be giving us output in between 0 and 1. We can keep some threshold. Let's say the threshold is 0.5. If you are getting greater than 0.5, then we can classify it as one class. And if it is less than 0.5, then we can keep it as other class, right? But let's say if you are trying to do some multi-class classification, let's first suppose it is 3-class classification. Then what is the number of neurons that we'll be having in the output layer? In such case, we'll be having 3 neurons like this. Each circle is representing 1 neuron over here. And these 3 neurons will be getting inputs from the previous layer. That is, this is the first neuron, right? So for this first neuron, we'll be getting the inputs from the previous layer, and all these inputs will get summed up and will be given to this particular neuron. Let's say that summed up information is represented with Z0. Like, let's say if it is O1, O2, O3, O4, the output that we get from these neurons, O6, all these will get multiplied with some weights and will get summed up to form Z0, right? And similarly, we'll be getting Z1, which is connecting this O1 to this particular second neuron, and O2 to this second neuron, O3 to the second neuron, O4 to the second neuron, O5 to the second neuron, and O6 to the second neuron. Like that, we'll be having Z1. Okay, so we'll be having Z1, and also we'll be having Z2 in case of this second neuron. Okay, like that, for each of these neurons in the output layer, we'll be having inputs like Z0 and then Z1 and Z2. And what, after applying softmax, what we'll expect? We'll expect that this will be giving the probability score for class 1, and this will be giving the probability score for class 2, and this will be giving the probability score for class 3. So this is what we expect, and softmax will help us in doing that. Basically, if we sum up all these probability scores after applying softmax, so let's say we have applied softmax over here, and after applying this softmax, we'll be getting these probability scores, and it will sum up to 1. In order to know what the model has predicted, we need to observe these probability scores individually, like P of class 1, probability of class 2, and probability of class 3, and whichever is maximum, that is our predicted output. Like that, we'll get to know what the model has predicted in case of multi-class classification. And how this particular score is getting calculated, that is simply getting calculated with the help of this particular formula, that is e power minus of Z0 in the numerator, whereas in denominator we'll be having all the Jedis. Here, in case of this, we are only having 3, so it will be e power Z0 plus e power Z1 plus e power Z2. But when we have more than 3, then it will be summation of all the e power minus Zis. And similarly here it will be minus e power Z1 and summation of e power minus Zis. And here it will be minus e power Z2 and summation of e power minus Zis. Like this, softmax activation function will work. So it will consider all of these. So, and it will be calculating the probability score for each of the classes. Okay. So I hope this softmax is clear for everyone. And after softmax, like these 3, we have discussed briefly in the previous videos also. But now let's go on to some other activation function, that is Tanh activation function. These all can be used on hidden layers as well, like linear and sigmoid can be used on hidden layers as well, along with these output layers based on the problem. And this tan h can also be used on hidden layers. So let's see what is this tan h function. So tan h of x is nothing but e power x minus e power of minus x, and in the denominator we'll be having e power x plus e power of minus x. So this is the formula for tan h of x, and here we might be passing input to be in any range, that is minus infinite to plus infinite, but the output that we will be getting will be in the range of minus 1 to plus 1. So whenever you wanted the output to be in this particular range, then it is better to use this particular tan h function. Okay, and let's see the graph of this particular tan h. So basically, as I said, on the x-axis we'll be having our input, that is x, and on y-axis we'll be having tan h of x. And as I said, the input can go from minus infinite to plus infinite, whereas the output will be ranging in between minus 1 to plus 1. Okay, so like this, our tan h function will be looking like. So this will be our minus 1, and this will be our plus 1. Okay, and if you check the derivative of tan h, that is tan h dash of x will be 1 minus tan h square of x. So this will be the derivative of tan h, and this can also be used on hidden layers, as I said. Okay, so this is about tan h activation function. And now let's see some other activation function, that is ReLU activation function. Full form of this is rectified linear units. This is really important. In most of the cases, in the hidden layers, we'll be using either ReLU or the next activation function that we'll be discussing, that is Leaky ReLU. Okay, we can use these as well, but by using this, it will cause some specific problem that we might be discussing in the next video. Okay, so that's why we'll be going to use this particular ReLU activation function in general. And what is this ReLU activation function? This ReLU activation function will work similar to linear activation function. Whenever x is greater than 0, we'll be outputting the same, that is x, but if x is less than or equal to 0, then we'll make it 0. Okay, so this is a ReLU activation function, and let's try to see it with the help of graph. So let's say this is our x and this is our ReLU of x, and according to this particular ReLU function that we have, if x is greater than 0, for 1 it will be giving 1, for 2 it will be giving 2, like that. Our line will be like this. Okay, if when x is greater than 0, but when x is less than or equal to 0, it will always be on 0. So this will be my ReLU graph, and at 0, ReLU function is not differentiable, and as it is only not differentiable at one point, we don't see it as a bigger problem. Okay, so this is about ReLU activation function. Now let's see the other last activation function that we are going to discuss, that is Leaky ReLU. So basically, in case of ReLU, whenever it is negative or 0, we are completely making it insignificant by making it to 0. So instead of that, the idea in Leaky ReLU is to multiply it with some smaller number. That is, whenever x is greater than 0, we'll leave it as it is. But whenever x is less than or equal to 0, instead of making completely equal to 0, we'll multiply with some alpha. And this alpha will be ranging in between 0 to 1. Okay. And this is also a happy parameter that we can decide. So let's say the alpha is some 0.0001. So this can be one possible alpha value. Okay, and the graph for this Leaky ReLU will be looking something like this. So on x-axis we'll be having x, on y-axis we'll be having this particular Leaky ReLU of x, and the corresponding graph will look like this. So whenever it is greater than 0, it will be the same as ReLU, but whenever it is less than 0, it will not reduce in the same proportion as X reduces, but it will slowly reduce. So this is about leaky ReLU activation function, and it is also not differentiable at 0. Okay, so these are all the different activation functions that we have discussed in this particular video. There are so many other activation functions as well, but most of the time we'll be using these as our activation functions. So I hope this video is clear for each and everyone. And if you have any doubts, please comment down in the comment section. I'll try to help you out. So thank you everyone. Bye bye.